Welcome to the second part of our Applied Chemistry series. Today, we'll be discussing fuels, which are essential to numerous industrial and domestic applications. We'll explore how fuels are classified, the principles of combustion, the importance of calorific value, and the methods used to determine the energy content of fuels using instruments like the Baum calorimeter and the Boyes gas calorimeter. So, let's dive into the fascinating world of fuels. First, let's define what we mean by fuels. Fuels are substances that release energy when they undergo combustion. This energy is essential for a variety of applications, including industrial processes, domestic heating, transportation, and electricity generation. Fuels can be classified based on their physical state and their source, and each type has its own advantages and limitations. One way to classify fuels is by their physical state. First, we have solid fuels, which are commonly used for domestic and industrial purposes. Examples of solid fuels include
coal, wood, peat, coke,
and lignite. Advantages of solid fuels include their ease of storage and transport, as well as their relatively low cost. However, they also have disadvantages, such as producing a significant amount of ash and pollutants during combustion, which can have negative environmental impacts. Next, we have liquid fuels, which are commonly used in transportation and for heating purposes. Examples include petrol, diesel, kerosene, and furnace oil. Advantages of liquid fuels include their high energy content and ease of handling. They burn cleaner than solid fuels and are more efficient. However, they also come with disadvantages. Liquid fuels tend to be more expensive than solid fuels, and they pose hazards in the event of spills, which can lead to environmental damage or safety risks. The third type of fuels is gaseous fuels, which are extensively used for domestic cooking, heating, and industrial processes. Examples of gaseous fuels include natural gas, liquefied petroleum gas (LPG), biogas, hydrogen, and producer gas. The advantages of gaseous fuels are that they have a high calorific value, burn cleaner than both liquid and solid fuels, and allow for easy control over combustion. However, they also have their disadvantages. Gaseous fuels require safe handling due to the risks of leakage and explosion, especially when stored or transported in pressurized containers. Fuels can also be classified based on their source. First, let's look at fossil fuels, which are derived from the remains of ancient organisms that decomposed over millions of years. Examples of fossil fuels include coal, oil, and natural gas. Advantages of fossil fuels include their high energy density and wide availability, making them the dominant energy source for industrial and transportation purposes. However, there are significant disadvantages. Fossil fuels are non-renewable, and their extraction and use contribute to environmental pollution, particularly in the form of greenhouse gas emissions. On the other hand, we have renewable fuels, which are derived from sustainable resources that can be replenished over time. Examples of renewable fuels include biomass, biofuels like ethanol and biodiesel, and biogas. The advantages of renewable fuels are that they are more environmentally friendly, with a lower impact on the environment compared to fossil fuels. They help reduce carbon emissions and can be sourced locally. However, renewable fuels also have their disadvantages, such as having a lower energy content than fossil fuels and being limited in availability in some regions. Combustion is the process by which a fuel reacts with oxygen to produce heat and other products such as carbon dioxide, CO2, and water, H2O. Combustion can be classified as complete combustion or incomplete combustion. Now, let's move on to the chemical principles involved in combustion. Complete combustion occurs when a fuel burns in the presence of sufficient oxygen, leading to the full oxidation of the fuel. The primary products of complete combustion are carbon dioxide, CO2, and water, H2O, along with the release of energy. For example, let's take the complete combustion of methane, CH4. The reaction is as follows. CH4 plus 2O2 gives CO2 plus 2H2O plus energy. This reaction shows that methane reacts with oxygen to produce carbon dioxide, water, and energy in the form of heat. Incomplete combustion, on the other hand, occurs when there is not enough oxygen present to fully oxidize the fuel. This leads to the formation of carbon monoxide, CO, soot, and other hydrocarbons, making the process less efficient and more hazardous. For example, in the incomplete combustion of methane, the reaction might look like this. 2CH4 plus 3O2 gives 2CO plus 4H2O plus energy. Here, instead of producing only CO2 and water, carbon monoxide, a toxic gas, is also formed. Incomplete combustion poses risks because carbon monoxide is harmful to human health and contributes to air pollution. Several key chemical principles are involved in the combustion process. Oxidation. This is the reaction between the fuel's carbon and hydrogen atoms with oxygen to form CO2 and H2O. Exothermic reaction. Combustion is an exothermic reaction, meaning it releases energy in the form of heat, which is why we rely on fuels for energy production. Stoichiometry. The ratio of fuel to oxygen is crucial for efficient combustion. Too little oxygen results in incomplete combustion, while too much oxygen can waste energy. Let's now move on to the concept of calorific value, which measures the amount of heat energy produced when a fuel undergoes combustion. It is an important property of fuels, as it determines their efficiency and energy content. There are two types of calorific values to consider. Gross calorific value, GCV, also known as the higher calorific value, is the total amount of heat produced when a fuel is burned, including the latent heat of vaporization of the water formed during combustion. Net calorific value, NCV, or the lower calorific value, excludes the heat of vaporization of water, resulting in a lower value than GCV. The difference between gross calorific value, GCV, and net calorific value, NCV, lies in the treatment of the water produced during combustion. GCV includes the heat released from the condensation of water vapor in the combustion products. In simpler terms, GCV accounts for all the heat produced, including the energy in the water vapor. NCV, on the other hand, excludes the heat released by the condensation of water vapor, focusing only on the energy that can be used directly. This makes NCV lower than GCV, as the energy in the water vapor is not considered in NCV calculations. The calorific value of fuels is usually expressed in terms of energy per unit of mass or volume, depending on the type of fuel. For solid and liquid fuels, calorific value is typically measured in kilojoules per kilogram. This unit tells us how much energy is produced per kilogram of fuel. For gaseous fuels, the calorific value is measured in kilojoules per cubic meter, reflecting the energy content per unit volume of the gas. The calorific value of a fuel can be determined using experimental devices like the Baum calorimeter and Boy's gas calorimeter. The Baum calorimeter consists of several key components. Combustion chamber. Baum, this is a strong, sealed chamber that contains the fuel sample and pure oxygen for combustion. Water jacket. The Baum is placed inside a water jacket, which is an insulated container filled with a known amount of water. The water absorbs the heat produced during combustion. Stirrer and thermometer. These components help to measure the rise in water temperature accurately. The stirrer ensures that the heat is evenly distributed, and the thermometer records the exact temperature increase. Let's now look at the working principle of the bomb calorimeter. A weighed sample of fuel is placed inside the bomb and ignited using an electric ignition system. The combustion occurs in an oxygen-rich environment, ensuring complete burning of the fuel. The heat produced by the combustion process is transferred to the surrounding water, causing a rise in the water temperature. By measuring this temperature rise, we can calculate the calorific value of the fuel, as the heat gained by the water is directly related to the energy released by the fuel. The gross calorific value, GCV, is calculated using the formula GCV equals W plus small w, delta T divided by M,
where
W equals mass of water in the calorimeter. Small w equals water equivalent of the calorimeter. Delta T equals temperature rise. M equals mass of fuel sample. Another device used for measuring the calorific value of fuels, particularly gaseous fuels, is the Boy's gas calorimeter. This instrument works on a similar principle to the bomb calorimeter but is specifically designed for measuring the heat content of gases. The Boy's gas calorimeter burns a known volume of gas, and the heat produced is transferred to a known quantity of water flowing through the system. The rise in water temperature is then measured to determine the calorific value of the gas. The Boy's gas calorimeter is constructed with several key parts. Combustion chamber. This is where the gas is burned. The chamber is designed to ensure complete combustion of the fuel. Water flow system. Water flows through the calorimeter in a controlled manner, absorbing the heat produced by the burning gas. Thermometers. These are placed before and after the water flow system to record the temperature change, which is used to calculate the calorific value of the gas. Here's how the Boy's gas calorimeter works. A known volume of gas is burned in the combustion chamber, releasing heat. This heat is transferred to the water flowing through the calorimeter, raising its temperature. By measuring the rise in water temperature, we can calculate the calorific value of the gas. Just like in the bomb calorimeter, the energy gained by the water reflects the energy released by the gas during combustion, allowing us to determine its efficiency and heat content. The calorific value of the gas is calculated using the formula GCV equals W delta T divided by V, where W equals mass of water heated, delta T equals temperature rise of water, V equals volume of gas burned. We've reached the end of our detailed exploration of fuels in applied chemistry. Throughout this video, we've covered different topics. Thank you for watching, and don't forget to subscribe for more tutorials on applied chemistry and other exciting topics.